Now there is another method which uses Laplacian eigenmaps to perform the factorization based approaches. Here first we go and look at what is the Laplacian matrix L. Laplacian matrix L is n cross n dimensional matrix which captures many useful properties of the graph. It is widely studied and it is matrix which can be constructed using the graph in following manner. So ijth element of the L, which is a Laplacian matrix, is difference between the ijth element of degree matrix and the ijth element of adjacency matrix, where I and j are the nodes belongs to V. So it is in principle difference between degree matrix minus adjacency matrix is giving a Laplacian matrix. So let's look at, for this example of graph which has a node 6 and edge 7, I have constructed Laplacian, which is difference between D and A. So you can see that degrees are preserved here, Z has only 1 degree, and similarly when some subtraction of A will provide us other elements, and this provides us Laplacian for this particular matrix, which is 6 by 6 matrix. Now we study the Laplacian matrix. We looked at what is the Laplacian eigenmaps. So what is Laplacian eigenmaps? So Laplacian eigenmaps are nonlinear dimensionality reduction technique which try to preserve local information on neighborhood relation between data points. So if I have a set of data points, the whole idea of using Laplacian eigenmaps is to preserve local information between data points and get the embedding. How it actually achieves? So how do you construct Laplacian from the data? So we are going to construct a graph of GV with nodes being a data points. So let me take data points. Let's say these are the data points. Okay. So each of this data point is my node. So I will draw a circle around each of them. Now I have to construct the edge, and I will construct the edge based on defining an epsilon neighborhood. So let me define epsilon neighborhood such that if I, for example, I define the epsilon neighborhood by constructing a circle with the center as a, not quite circle. Okay. Okay. For this particular point, I will define the epsilon distance being this one, and I can construct a circle which tells me what are the nodes for which I should actually have a edge, and I can keep doing it, and it will provide me edge between different points. So this one is there, this one, this one. And this way I got my graph, and for this graph I am going to define, so this is data which I converted into graph, to the graph, and then I will define my L Laplacian matrix on that. Once I have Laplacian matrix, what I am going to do is I am going to learn embedding. How I can learn embedding? By minimizing the objective function, where for each y I represent embedding for the point I and j with a weighting being a Lij, and which minimizes subject to these two constraints, where y transpose dy is equal to 1 and y transpose d is into 1 is equal to 0. We are not going to go to detail why these constraints are needed, but for the sake of finding a tractable solution, we are going to keep this constraint. Otherwise, we have to perform some more additional analysis to find a non-trivial solution. The solution here is compute the eigenvalue and eigenvector for the generalized eigenvector problem Ly equal to lambda dy. Recall, if d is equal to I, then it will become a standard eigenvector problem, finding out the eigenvector for Laplacian matrix L, which is constructed using the previous analogy of epsilon neighborhood with age. However, in certain cases we cannot find d is equal to I. In that case, it is going to be generalized eigenvector problem. And how we can find eigen embedding? The embedding here is the eigenvector corresponding to the r smallest non-zero eigenvalue, which we found by minimizing this particular objective function or loss function. One thing, remember that if we do not put this constraint, we will have 0 as a solution, which is for any Laplacian is true, 0 as a singular smallest eigenvalue for the Laplacian, and that's why I am writing m non-zero smallest eigenvalue, which we can avoid by reformulating the problem, and that gives us a Laplacian Eigenmaps. And the embedding here is of n cross r dimensional matrix. So I took first smallest r eigenvalues and corresponding eigenvector and stack them in a column. So 1, 2, 3, 4 to I r. So this y has each column has a one eigenvector correspond to each smallest non-zero value, and this one y is n cross n, where n are number of points, and this is the lower dimensional embedding. Now you have got an idea that I can do the same analysis if I have a graph instead of points. So what we are going to do is we are going to use the same idea here. Remember that yi and yj, we are interested here is, instead of in a decoder function, we are interested in minimizing zu and zv as distance between them, instead which was here yi minus yj. So if we do that, our loss function here is going to be decoder zu zv for each pair into some similarity which is weighted similarity. Here we are, instead of using adjacency matrix, we can use Laplacian matrix of this particular graph, and this will lead us to a same formulation as a Laplacian Eigenmaps. Here you remember that this particular maps penalizes the model when similar nodes have embedding that are far apart. So it will ensure that if there are two similar nodes, which is a far apart embedding, the S will ensure that that kind of case does not happen, because it will penalize your system. Think that if there is a element 1 here, and if Z and U are nearby, but U and V are nearby, but in embedding space we put it very far, then it will penalize accordingly. It will actually magnify accordingly. So this particular formulation ensures that we have if U and V are close by nodes in a graph, then that particular structure is preserved while performing the embedding tasks. Now, as we discussed, if ZU is a D-dimensional or here D or R-dimensional and S is Laplacian, then the solution that minimizes this particular loss function is the D smallest eigenvector of Laplacian matrix, okay, excluding the eigenvectors of 1, which is basically what we have seen in this particular example. We are excluding that. So, by taking this as an embedding and S as a Laplacian, we can again perform embedding in this particular case. Now, how we can actually find solution for low rank matrix factorization? We can use singular value decomposition to do that. Remember, all of these problems are of the same form, Z transpose minus S, and we try to perform Frobenius norm minimization. Here we are interested in finding out Z transpose such that it minimizes this loss function. What we can do is we can actually perform SVD of S, because we know that we can find a lower dimensional representation of S which is lower than rank of S. So how we can compute? We can compute SVD of S and keep top D values for all the three matrices. Z transpose equal to it's approximately SD, US, UD, DD, VD transpose in any matrix factorization based approaches or inner product based approaches. In case of Laplacian, we have to do little differently as we discussed, but we still can apply SVD. And as I told you, how we can do is we decompose S into U, D and V transpose, where we only take first top D values when it comes to inner product based methods and get Z transpose based on decomposing. This can be written as Z transpose. Remember that this is D will be diagonal matrix. Hence, in all the matrix factorization or factor based approaches, we can use singular value decomposition as an approach. Of course, there are limitations in certain applications. Applying SVD will be computational costly, and hence people are also using, or researchers are also using, stochastic gradient descent methods. So let me summarize today's let me summarize factorization based methods or approaches. We have looked at Laplacian Eigenmaps, graph factorization, graph grep and hope, where we have seen that the last three methods use inner product based decoder, while the Laplacian eigenvalue, Laplacian eigenmaps based method use the difference between two embedded vectors square minimization or L2 norm square minimization. Similarity measure in a Laplacian eigenmaps is obviously Laplacian matrix. In case of graph factorization, it's the adjacency matrix. In graph rep, it is some scaled adjacency matrix, and in a hope it is a higher order proximity measures. The loss function in this case is defined as a inner product of Laplacian and the decoder function. Here it is a L2 norm of decoder function and similarity function for these two methods. So with this, I would like to thank you.